Hello guys and welcome. This is my first stream. Today we're going to read the Ethereum Whitepaper. Let's dive in. This introductory paper was originally published in 2013 by Vitalik Buterin, the founder of Ethereum, before the project's launch in 2015. It's worth noting that Ethereum, like many community-driven open source software projects, has evolved since its initial inception. While several years old, we maintain this paper because it continues to serve as a useful reference and an accurate representation of Ethereum and its vision. To learn about the latest developments of Ethereum and how changes to the protocol are made, we can follow a different guide. It's a next-generation smart contract and decentralized application platform. Satoshi Nakamoto's development of Bitcoin in 2009 has often been hailed as a radical development in money and currency, being the first example of a digital asset which simultaneously has no backing or intrinsic value, and no centralized issuer or controller. However, another arguably more important part of the Bitcoin experiment is the underlying blockchain technology as a tool of distributed consensus. And attention is rapidly starting to shift to this other aspect of Bitcoin. Commonly cited alternative applications of blockchain technology, including using on-blockchain digital assets to represent custom currencies and financial instruments. The ownership of an underlying physical device, non-fungible assets such as domain names, as well as more complex applications involving having digital assets being directly controlled by a piece of code implementing arbitrary rules or smart contracts, or even blockchain-based decentralized autonomous organizations. What Ethereum intends to provide is a blockchain with a built-in, fully-fledged, Turing-complete programming language that can be used to create contracts that can be used to encode arbitrary state transition functions, allowing users to create any of the systems described above, as well as many others that we have not yet imagined, simply by writing up the logic in a few lines of code. The concept of decentralized digital currency, as well as alternative applications like property registries, has been around for decades. The anonymous e-cash protocols of the 1980s and the 1990s, mostly reliant on a cryptographic primitive known as a Chaumian blinding, provided a currency with a high degree of privacy, but the protocols largely failed to gain traction because of their reliance on a centralized intermediary. In 1998, Wei Dai's B-money became the first proposal to introduce the idea of creating money through solving computational puzzles as well as decentralized consensus. But the proposal was scant on details as to how decentralized consensus could actually be implemented. In 2005, Hal Finney introduced the concept of reusable proofs of work, a system which uses ideas from B-money together with Adam Back's computationally difficult Hashcash puzzles to create a concept for a cryptocurrency, but once again fell short of the ideal by relying on trusted computing as a backend. In 2009, a decentralized currency was for the first time implemented in practice by Satoshi Nakamoto, combining established primitives for managing ownership through public key cryptography with a consensus algorithm for keeping track of who owns coins, known as proof of work. The mechanism behind proof of work was a breakthrough in the space because it simultaneously solved two problems. First, it provided a simple and moderately effective consensus algorithm, allowing nodes in the network to collectively agree on a set of canonical updates to the state of the Bitcoin ledger. Second, it provided a mechanism for allowing free entry into the consensus process, solving the political problem of deciding who gets to influence the consensus, while simultaneously preventing Sybil attacks. It does this by substituting a formal barrier of participation, such as the requirement to be registered as a unique entity on a particular list. With an economic barrier, the weight of a single node in the consensus voting process is directly proportional to the computing power that the node brings. Since then, an alternative approach has been proposed called proof of stake, calculating the weight of a node as being proportional to its currency holdings and not computational resources. The discussion of the relative merits of the two approaches is beyond the scope of this paper, but it should be noted that both approaches can be used as the backbone of a cryptocurrency. From a technical standpoint, the ledger of a cryptocurrency such as Bitcoin can be thought of as a state transition system. where there is a state consisting of the ownership status of all existing bitcoins and a state transition function that takes a state and a transaction and outputs a new state, which is the result. In a standard banking system, for example, the state is a balance sheet. A transaction is a request to move X amount of money from A to B, and the state transition function reduces the value in A's account by X amount of dollars and increases the value in B's account by the same amount. If A's account has less than X amount of dollars in the first place, the state transition function returns an error. Hence, one can formally define these codes here. We're not going to get into the specifics of that. You can see it right here though. The state in Bitcoin is the collection of all coins, technically unspent transaction outputs, or UTXO, that have been mined and not yet spent, with each UTXO having a denomination and an owner defined by a 20-byte address, which is essentially a cryptographic public key. A transaction contains one or more inputs, with each input containing a reference to an existing UTXO and a cryptographic signature produced by the private key associated with the owner's address, and one or more outputs, with each output containing a new UTXO to be added to the state. For each input in transaction, if the reference UTXO is not in S, it will return an error. If the provided signature does not match the owner of the UTXO, it will return an error. If the sum of the denominations of all input UTXO is less than the sum of the denominations of all output UTXO, it will also return an error. If it returns S with all input UTXO removed and all output UTXO is added. The first half of the step prevents transaction senders from spending coins that do not exist. The second half of the first step prevents transaction senders from spending other people's coins, and the second step enforces conservation of value. In order to use this for payment, the protocol is as follows. Suppose Alice wants to send 11.7 Bitcoin to Bob. First, Alice will look for a set of available UTXO that she owns that totals up to at least 11.7 Bitcoin. Realistically, Alice will not be able to get exactly 11.7 Bitcoin. Say that the smallest she can get is 12. She then creates a transaction with those three inputs and two outputs. The first output will be 11.7 Bitcoin with Bob's address as its owner, and the second output will be the remaining 0.3 Bitcoin or change, with the owner being Alice herself. If we had access to a trustworthy centralized service, this system would be trivial to implement. It would simply be coded exactly as described, using a centralized server's hard drive to keep track of the state. However, with Bitcoin, we are trying to build a decentralized currency system, so we will need to combine the state of the transition system with a consensus system in order to ensure that everyone agrees on the order of the transactions. Bitcoin's decentralized consensus process requires nodes in the network to continuously attempt to produce packages of transactions called blocks. The network is intended to produce roughly one block every 10 minutes, with each block containing a timestamp or a nonce, which is a number once, a reference to or hash of the previous block, and a list of all of the transactions that have taken place since the previous block. Over time, this creates a persistent, ever-growing blockchain that constantly updates to represent the latest state of the Bitcoin ledger. The algorithm for checking if the block is valid, expressed in this paradigm, is as follows. Check if the previous block referenced by the block exists and is valid. Check that the timestamp of the block is greater than that of the previous block and less than 2 hours into the future. Check that the proof of work on the block is valid. Let S bracket 0 bracket be the state at the end of the previous block. And suppose transaction is the block's transaction list with n transactions. This is a bit of code, guys. We'll skip through that. Essentially, each transaction in the block must provide a valid state transition from what was the canonical state before the transaction was executed to some new state. Note that the state is not encoded in the block in any way. It is purely an abstraction to be remembered by the validating node and can only be securely computed for any block by starting from the genesis state and sequentially applying every transaction in every block. Additionally, note that the order in which the miner includes transaction into the block matters. If there are two transactions A and B in a block such that B spends a UTXO created by A, then the block will be valid if A comes before B but not otherwise. The one validity condition present in the above list that is not found in other systems is the requirement for proof of work. The precise condition is that the double SHA 256 hash of every block treated as a 256-bit number must be less than a dynamically adjusted target, which is, as of the time of this writing, is approximately 2 to the power of 187. The purpose of this is to make every block creation computationally hard, thereby preventing Sybil attackers from remaking the entire blockchain in their favor. Because SHA 256 is designed to be a completely unpredictable pseudo-random function, the only way to create a valid block is simply trial and error, repeatedly incrementing the nonce and seeing if the new hash matches. At the current target of 2 to the power of 187, the network must make an average of 2 to the power of 69 tries before a valid block is found. In general, the target is recalibrated by the network every 2016 blocks, so that on average a new block is produced by some node in the network every 10 minutes. In order to compensate miners for this computational work, the miner of every block is entitled to include a transaction giving themselves 12.5 Bitcoin out of nowhere. Additionally, if any transaction has a higher total denomination in its inputs than its outputs, the difference also goes to the miner as a transaction fee. Incidentally, this is also the only mechanism by which Bitcoin are issued. The Genesis state contained no coins at all. In order to better understand the purpose of mining, let us examine what happens in the event of a malicious attacker. Since Bitcoin's underlying cryptography is known to be secure, the attacker will target the one part of the Bitcoin system that is not protected by cryptography directly, the order of transactions. The attacker's strategy is simple. Send 100 Bitcoin to a merchant in exchange for some product, preferably a rapid delivery digital good, wait for the delivery of the product, produce another transaction sending the same 100 Bitcoin to himself, try to convince the network that his transaction to himself was the one that came first. Once step 1 has taken place, after a few minutes some miner will include the transaction in a block, say block number 270. After about 1 hour, 5 more blocks will have been added to the chain after that block, with each of those blocks indirectly pointing to the transaction and thus confirming it. At this point, the merchant will accept the payment as finalized and deliver the product. Since we are assuming that this is a digital good, delivery is instant. Now, the attacker creates another transaction sending the 100 Bitcoin to himself. If the attacker simply releases it into the wild, the transaction will not be processed. Miners will attempt to run the code and notice that the transaction tag consumes a UTXO which is no longer in the state. So instead, the attacker creates a fork of the blockchain, starting by mining another version of block 270, pointing to the same block 269 as a parent, but with the new transaction in place of the old one. Because the block data is different, this requires redoing the proof of work. Furthermore, the attacker's new version of block 270 has a different hash, so the original blocks 271 to 275 do not point to it. Thus, the original chain and the attacker's new chain are completely separate. The rule is that in a fork, the longest blockchain is taken to be the truth. So the legitimate miners will work on the 275 chain while the attacker alone is working on the 270 chain. In order for the attacker to make his blockchain the longest, he would need to have more computational power than the rest of the network combined in order to catch up, hence a 51% attack. We can see Merkle trees here. An important scalability feature of Bitcoin is that the block is stored in a multi-level data structure. The hash of a block is actually only the hash of the block header, a roughly 200-byte piece of data that contains the timestamp, nonce, previous block hash, and the root hash of a data structure called the Merkle tree, storing all transactions in the block. A Merkle tree is a type of binary tree, composed of a set of nodes with a large number of leaf nodes at the bottom of the tree containing the underlying data, a set of intermediate nodes where each node is the hash of its two children, and finally a single root node also formed from the hash of its two children, representing the top of the tree. The purpose of the Merkle tree is to allow the data in a block to be delivered piecemeal. A node can download only the header of a block from one source, the small part of the tree relevant to them from another source, and still be assured that all of the data is correct. The reason why this works is that hashes propagate upward. If a malicious user attempts to swap in a fake transaction into the bottom of a Merkle tree, this change will cause a change in the node above, and then a change in the node above that. finally changing the root of the tree and therefore the hash of the block, causing the protocol to register it as a completely different block, almost certainly with an invalid proof of work. The Merkle tree protocol is arguably essential to long-term sustainability. A full node in the Bitcoin network, one that stores and processes the entirety of every block, takes up about 15 gigabytes of disk space in the Bitcoin network as of April 2014, and is growing by over a gigabyte per month. Currently, this is viable for some desktop computers and not phones, and later on in the future, only businesses and hobbyists will be able to participate. A protocol known as Simplified Payment Verification, or SPV, allows for another class of nodes to exist called light nodes, which download the block headers, verify the proof of work on the block headers, and then download only the branches associated with the transactions that are relevant to them. This allows light nodes to determine with a strong guarantee of security that the status of any Bitcoin transaction and their current balance is while downloading only a very small portion of the blockchain. Alternative blockchain applications. The idea of taking the underlying blockchain idea and applying it to other concepts also has a long history. In 1998, Nick Szabo came out with the concept of secure property titles with the owner authority, a document describing how new advances in replicated database technology will allow for a blockchain-based system for storing a registry of who owns what land, creating an elaborate framework including concepts such as homesteading, adverse possession, and Georgian land tax. However, there was unfortunately no effective replicated database system available at the time, and so the protocol was never implemented in practice. After 2009, however, once Bitcoin's decentralized consensus was developed, a number of alternate applications rapidly began to emerge. Namecoin. Created in 2010, Namecoin is best described as a decentralized name registration base. In decentralized protocols like Tor, Bitcoin, and BitMessage, there needs to be some way of identifying accounts so that other people can interact with them, but in all existing solutions, the only kind of identifier available is a pseudo-random hash with a random string of letters and numbers. Ideally, one would like to be able to have an account with a name like George. However, the problem is that if one person can create an account named George, then someone else can use the same account and impersonate the other George. The only solution is a first-to-file paradigm, where the first register succeeds and the second fails, a problem perfectly suited for the Bitcoin consensus protocol. Namecoin is the oldest and most successful implementation of a name registration system using such an idea. Colored coins. The purpose of colored coins is to serve as a protocol to allow people to create their own digital currencies, or, in the important trivial case of a currency with one unit, digital tokens, on the Bitcoin blockchain. In the colored coins protocol, one issues a new currency by publicly assigning a color to a specific Bitcoin UTXO, and the protocol recursively defines the color of the other UTXO to be the same as the color of the inputs that the transaction creating them spent. Some special rules apply in the case of mixed color inputs. This allows users to maintain wallets containing only UTXO of a specific color and then send them around much like regular Bitcoins, backtracking through the blockchain to determine the color of any UTXO that they receive. Metacoins. The idea behind a metacoin is to have a protocol that lives on top of Bitcoin, using Bitcoin transactions to store metacoin transactions, but having a different state transition function known as apply. Because the metacoin protocol cannot prevent invalid metacoin transactions from appearing in the Bitcoin blockchain, a rule is added that if apply, that's just code, it will return an error. The protocol defaults to more code, and this provides an easy mechanism for creating an arbitrary cryptocurrency protocol, potentially with advanced features that cannot be implemented inside of Bitcoin itself, but with a very low development cost since the complexities of mining and networking are already handled by the Bitcoin protocol. Metacoins have been able to implement some classes of financial contracts, name registration, and decentralized exchange. Thus, in general, there are two approaches toward building a consensus protocol: building an independent network and building a protocol on top of Bitcoin. The former approach, while reasonably successful in the case of applications like Namecoin, is difficult to implement. Each individual implementation needs to bootstrap an independent blockchain, as well as building and testing all the necessary state transition and networking code. Additionally, we predict that the set of applications for decentralized consensus technology will follow a power law distribution where the vast majority of applications will be too small to warrant their own blockchain. And we note that there exist large classes of decentralized applications, particularly decentralized autonomous organizations that need to interact with each other. The Bitcoin-based approach, on the other hand, has the flaw that it does not inherit the simplified payment verification features of Bitcoin. SPV works for Bitcoin because it can use blockchain depth as a proxy for validity. At some point, once the ancestors of a transaction go back far enough, it is safe to say that they were legitimately part of the state. Blockchain-based meta protocols, on the other hand, cannot force the blockchain not to include transactions that are not valid within the context of their own protocols. Hence, a fully secure SPV meta protocol implementation would need to backward scan all the way to the beginning of the Bitcoin blockchain to determine whether or not certain transactions are valid. Currently, all light implementations of Bitcoin-based meta protocols rely on a trusted server to provide the data, arguably a highly suboptimal result, especially when one of the primary purposes of a cryptocurrency is to eliminate the need for trust. Scripting. Even without any extensions, the Bitcoin protocol actually does facilitate a weak version of a concept called smart contracts. UTXO in Bitcoin can be owned not just by a public key, but also by a more complicated script expressed in a simple stack-based programming language. In this paradigm, a transaction spending that UTXO must provide data that satisfies the script. Indeed, even the basic public key ownership mechanism is implemented via a script. The script takes an elliptic curve signature as input, verifies it against the transaction and the address that owns the UTXO, and returns 1 if the verification is successful and 0 otherwise. Other, more complicated scripts exist for various additional use cases. For example, one can construct a script that requires signatures from 2 out of a given 3 private keys to validate, or multisig. A setup useful for corporate accounts, secure savings accounts, and some merchant escrow situations. Scripts can also be used to pay bounties for solutions to computational problems, and one can even construct a script that says something like, "This Bitcoin UTXO is yours if you can provide an SPV proof that you sent a Dogecoin transaction of this denomination to me," essentially allowing decentralized cross-cryptocurrency exchange. However, the scripting language as implemented in Bitcoin has several important limitations. Lack of Turing completeness, that is to say, while there is a large subset of computation that the Bitcoin scripting language supports, it does not nearly support everything. The main category that is missing is loops. This is done to avoid infinite loops during transaction verification. Theoretically, it is a surmountable obstacle for script programmers since any loop can be simulated by simply repeating the underlying code many times with an if statement. But it does lead to scripts that are very space inefficient. For example, implementing an alternative elliptic curve signature algorithm would likely require 256 repeated multiplication rounds, all individually included in the code. Value blindness. There is no way for a UTXO script to provide fine-grained control over the amount that can be withdrawn. For example, one powerful use case of an Oracle contract would be a hedging contract, where A and B put in $1,000 worth of Bitcoin, and after 30 days, the script sends $1,000 worth of Bitcoin to A and the rest to B. This would require an oracle to determine the value of 1 Bitcoin in US dollars. But even then, it is a massive improvement in terms of trust and infrastructure requirement over the fully centralized solutions that are available now. However, because UTXO are all or nothing, the only way to achieve this is through the very inefficient hack of having many UTXO of varying denominations. For example, one UTXO of 2 to the power of k for every k up to 30, and having O pick which UTXO to send to A and B. Lack of state. A UTXO can either be spent or unspent. There is no opportunity for multi-stage contracts or scripts which keep any other internal state beyond that. This makes it hard to make multi-stage options contracts, decentralized exchange offers, or 2-stage cryptographic commitment protocols necessary for secure computational bounties. It also means that UTXO can only be used to build simple one-off contracts and not more complex stateful contracts such as decentralized organizations, and makes meta protocols difficult to implement. Binary state combined with value blindness also mean that another important application, withdrawal limits, is impossible. Blockchain blindness. UTXO are blind to blockchain data such as the nonce, the timestamp, and previous block hash. This severely limits applications in gambling and several other categories. By depriving the scripting language of a potentially valuable source of randomness. Thus, we see three approaches to building advanced applications on top of cryptocurrency: building a new blockchain using scripting on top of Bitcoin, and building a meta protocol on top of Bitcoin. Building a new blockchain allows for unlimited freedom in building a feature set, but at the cost of development time, bootstrapping effort, and security. Using scripting is easy to implement and standardize, but is very limited in its capabilities, and meta protocols, while easy, suffer from faults in scalability. With Ethereum, we tend to build an alternative framework that provides even larger gains in case of development, as well as even stronger light client properties, while at the same time allowing applications to share an economic environment and blockchain security. The intent of Ethereum is to create an alternative protocol for building decentralized applications, providing a different set of trade-offs that we believe will be very useful for a large class of decentralized applications, with particular emphasis on situations where rapid development time, security for small and rarely used applications, and the ability of different applications to very efficiently interact are important. Ethereum does this by building what is essentially the ultimate abstract foundational layer, a blockchain with a built-in Turing-complete programming language, allowing anyone to write smart contracts and decentralized applications where they can create their own arbitrary rules for ownership. The transaction formats and state transition functions. A bare bones version of Namecoin can be written in 2 lines of code, and other protocols like currencies and reputation systems can be built in under 20. Smart contracts, cryptographic boxes that contain value and only unlock if certain conditions are met, can also be built on top of the platform, with vastly more power than that offered by Bitcoin scripting because of the added powers of Turing completeness, value awareness, blockchain awareness, and state. Philosophy. The design behind Ethereum is intended to follow the following principles. Simplicity. The Ethereum protocol should be as simple as possible, even at the time of some data storage or time inefficiency. An average programmer should ideally be able to follow and implement the entire specification so as to fully realize the unprecedented democratizing potential that cryptocurrency brings, and further the vision of Ethereum as a protocol that is open to all. Any optimization which adds complexity should not be included unless the optimization provides very substantial benefit. Universality. A fundamental part of Ethereum's design philosophy is that Ethereum does not have features. Instead, Ethereum provides an internal Turing-complete scripting language which a programmer can use to construct any smart contract or transaction type that can be mathematically defined. Want to invent your own financial derivative? With Ethereum, you can. Want to make your own currency? Set it up as an Ethereum contract. Want to make a full-scale daemon or Skynet? You may need to have a few thousand interlocking contracts and be sure to feed them generously to do that, but nothing is stopping you with Ethereum at your fingertips. Modularity. The parts of the Ethereum protocol should be designed to be as modular and separable as possible. Over the course of development, our goal is to create a program where if one was to make a small protocol modification in one place, the application stack would continue to function without any further modification. Innovations such as ET hash, see the yellow paper appendix in the wiki article on, you guys can check that out if you follow the link at the top of the screen. Modified Patricia Screes and RLP should be and are implemented as separate feature-complete libraries. This is so that even though they are used in Ethereum, even if Ethereum does not require certain features, such features are still usable in other protocols as well. Ethereum development should be maximally done so as to benefit the entire cryptocurrency ecosystem, not just itself. Agility. Details of the Ethereum protocol are not set in stone, although we will be extremely judicious about making modifications to high-level constructs, for instance with the sharding roadmap, abstracting execution with only data availability enshrined in consensus. Computational tests later on in the development process may lead us to discover that certain modifications, example to the protocol, architecture, or to the Ethereum virtual machine, will substantially improve scalability or security. If any such opportunities are found, we will exploit them. Non-discrimination and non-censorship. The protocol should not attempt to actively restrict or prevent specific categories of usage. All regulatory mechanisms in the protocol should be designed to directly regulate the harm and not attempt to oppose specific undesirable applications. A programmer can even run an infinite loop script on top of Ethereum for as long as they are willing to keep paying the per computational step transaction fee. In Ethereum, the state is made up of objects called accounts, with each count having a 20-byte address and state transitions being direct transfers of value and information between accounts. An Ethereum account contains four fields. The nonce account are used to make sure each transaction can only be processed once, the account's current ether balance, the account's contract code, if present, the account's storage, empty by default, and Ether is the main internal crypto fuel of Ethereum and is used to pay transaction fees. In general, there are two types of accounts: externally owned accounts controlled by private keys and contract accounts controlled by the contract code. An externally owned account has no code, and one can send messages from an externally owned account by creating and signing a transaction in a contract account. Every time the contract account receives a message, its code activates, allowing it to read and write in internal storage and send other messages or create contracts in turn. Note that contracts in Ethereum should not be seen as something that should be fulfilled or complied with. Rather, they are more like autonomous agents that live inside of the Ethereum execution environment, always executing a specific piece of code when poked by a message or transaction, and having direct control over their own ether balance and their own key value store to keep track of persistent variables. And with that, guys, we are going to end the video and we will continue after the break.